Now let's talk about subspaces. They will actually be the most important concepts for us until the end of the course. So let's start with the definition. A subspace W of a vector space V is a set of vectors that satisfies two requirements. So what do we need? We need V and W to be two vectors inside W, and C to be any scalar. If these conditions are satisfied, so if we take two vectors in W and a scalar, then W is closed under addition and scalar multiplication. What does that mean? It means that the sum of V plus W is also in W, and the new vector C times V is also in W. I kind of like to look at this with a little picture diagram. So imagine you have the vector space V somehow here, and then you have the vector space W over here. So W must be, first of all, a subset of V, because this is also a set. So if I take two vectors, V and W, which are inside the subset W, then the first rule says that their sum, when you add them up, V plus W, is still inside the subspace W. It's not outside, it's not here. You cannot add these two vectors and get out of the subspace. If you do, then you didn't have a subspace to begin with. And then the second rule says that if you've taken a vector V in W, well, when you multiply it by some scalar, CV is also going to be in W. So you have that closure under addition and scalar multiplication. Now, if we think a little bit about this, we see that we have an equivalent condition. So let me make a claim here. If W is a subspace of V, and U and V are vectors in W, then we can actually take their linear combination, CU plus DV must also be in W. And note here that I'm not choosing a particular constant C or D. It could be anything. Why is this the case? Why can we conclude this from rules 1 and 2? Well, I know that if U is in the subspace, then by rule 2, I have C times U is also in W. If V is in W, then dV is also in W. So putting these two together, we have two new vectors. We have a vector CU and a vector dV. Well, then let's use the first rule, which talks about the sum of two vectors. So if you have the vectors V and W in the space, then their sum is also in the space. So by the first rule, from here, CU plus dV is also in W. So in other words, we can change these two conditions to actually mean, or an equivalent way, to state these two conditions. So an equivalent way would be to say that CV plus dW is in W for any scalars C and D, right? We have to include that scalar D. So you could look at the two rules where you have the sum of a vector and this scalar multiple of vectors. If you have those two rules, it's the same as saying that you actually have all linear combinations in the subspace. And this actually gives us a way to think about creating subspaces. So how would you generate a subspace given some vector space? So if I have a vector space V, all I need to do is I could just take one vector and create a space. I could add that vector to itself as many times as I like and create more vectors. Or that is the equivalent thing to multiplying that vector by some scalar, by any scalar really, any number, and I'm going to get infinitely many vectors that are going to respect this structure. So, which is the same thing as talking about linear combinations, it's just that when you have only one vector, they kind of boil down to multiply the vector by some scalar, you're going to get a new vector in the space. And this is exactly the types of subspaces that we would get when we would say, okay, what is the subspace represented by all linear combinations of a single vector? Well, we had a line. So let me make that a bit more formal. Let me write it down. Let's talk about, as an example, the subspaces of, let's say, R3. Oh, one important thing that I forgot to mention is that because we are allowed to choose any scalar, in particular, we are allowed to choose the scalar 0. So if you want a subset, W, to be a subspace, you have to have the 0 vector in there. So no matter what, we always have the 0 vector. Why? Because the 0 vector is simply 0 times V. So when you just choose C to equal 0, you get the 0 vector. So every subspace of a vector space V must contain the 0 vector. And in fact, that's the first, the first subspace of R3. So we could take the 0 vector, right? This is the set that contains only the 0 vector. And when you have only the 0 vector, if you look here in the rules, there is nothing about not respecting these two rules. You take the 0 vector, add it with itself, you're going to get the 0 vector again. So you see that the set containing only the 0 vector is definitely closed under addition. And if you multiply the 0 vector by some number, you're going to get the 0 vector. So it is absolutely true that C times V is again an element of the subspace. So the 0 vector is going to be, or the set containing the 0 vector is a subspace of every vector space. It's just that we have to be a little flexible as to what that 0 vector means. In R3, it means the vector with 3 components, all of which are 0. If we had R5, we would have talked about a vector with 5 components. If we had the function space, we would talk about a function of the 0 function. If we had a matrix, we would talk about a matrix with 0 components inside. So that 0 vector really depends on the context. Another trivial space is really, or trivial subspace, is the space itself. So the entire space R3 is trivially a subset of itself, or a subset. And because it's a space, it's also a subspace. It certainly respects linear combinations. Another type of subspace that we could have is L, which is any line through the origin. Now you understand why we need that origin, because if we don't have the origin, we would not be able to multiply by the constant 0, which we want to be able to do. So any line through 0, 0, 0 is going to give us a subspace of R3. And we also have P, which is a plane through the origin. this is, in fact, quite interesting that you have R3. Any line, if you just consider we have a line here, and we take two vectors along that line, so remember that we represented vectors as arrows from the origin, and it's nice that we have the origin here, for example. So you take one vector here and maybe another, I don't know, this color looks nice, another vector along that same line. The sum will continue to be on the line. You could take that green vector to be in the opposite direction. It will not matter. Their sum, or whatever linear combination you take of those two vectors, they're going to exist on that line. And the same is true for a plane. So if we have a plane in 3D space passing through the origin, so here's the origin, then when you take any two vectors in the plane, their sum is also going to be in the plane. If you remember when we added vectors, they're just going to give us sort of a parallelogram which will lie on that plane because the two vectors, the green and the blue vector, are on that plane. If you don't have the origin, you do not have a vector space. And of course, when you have a plane that is a subspace, there are many vectors that will not be on that plane. Now, let's look at another example of subspaces. I'll go back to green. So let's talk about, so we talked about the vector space M. Inside the vector space M, remember this was the vector space of all 2 by 2 real matrices. We have the following subspaces. This is not an exhaustive list. There are more, but here are just two of them. So we have U, which is all upper triangular matrices. And D, the subspace consisting of all diagonal matrices. Let's see why that is the case. So what do we have to check to make sure that this set, so for starters, let's think of U as a set that contains all upper triangular matrices. What we have to check is whether, when we take a linear combination of two upper triangular matrices, we're going to get another upper triangular matrix. So let's see, C times the matrix, well, I want to use that C for something else. So let's take two matrices, A, B, C, and we have to have a 0 under the diagonal. So maybe I'll call the first scalar alpha 1 or alpha, and the second scalar can be beta, and then here I can have another matrix E, F, G, 0. Well, the way scalar multiplication works and matrix addition, I know that this alpha A and beta E will add up, alpha B and beta F, and alpha C and beta G. The key point is that whatever the answer is, there is a 0 here. So you see, when you take two upper triangular matrices and then take a linear combination of them, you're going to get an upper triangular matrix. That tells you that the set of all upper triangular matrices generates or represents a vector subspace of the vector space M of all 2 by 2 matrices. By a very similar argument, you can replace upper triangular with lower triangular and get the same answer. And in fact, when you put those two together, you get the space of all diagonal matrices. So you have a matrix here, A, B, 0, 0, right? It's a diagonal matrix. and you add it to another matrix CD with zeros. You can add whatever constants you want here, alpha and beta. And no matter the addition, we know we're going to have two zeros here and something non-zero along the diagonal. So you see that when you take two diagonal matrices, whatever linear combination you take of those two matrices will again be a diagonal matrix. So the set of all diagonal matrices is indeed a subspace of M. You will see more examples in the suggested problems.